Are we okay with that? All right. Now, the other thing is we then have to say, all right, well, what if it's not a number? It could be an array of type any. So that's the syntax for writing an array of type any. Right? So it's going to, you notice it's a mix of different things. So it will always sort of promote to the least common denominator, or in this case, any. All right, so now what? We know we've already handled this case. Let's actually check things off. We've written the concrete syntax. We gave you the lexical analyzer. We're working on the parser. And we've handled the number case. All right, so now we're handling these two cases. So what's the first thing we want to do? Yeah.
Check the symbol.
Look at the symbol. We've determined it's one of these two. Here's how we're going to tell the difference. So if expression 1, not 0, 1, is the plus symbol, so in other words, as in this example, it's the plus symbol here, and that's the syntactic way for writing a symbol in Julia is colon the symbol. If it's the plus symbol, what do we want to do?
Return plus node.
Yeah, return a plus node. Okay, now plus node takes a left-hand side and a right-hand side here. What do we want to put in for those?
Would be expression 2 and 3.
Yeah. So let's go with this for just a minute, and then we'll come back. Expression 2, expression 3. Okay. And otherwise, we can do an else if 1 equals minus symbol. We'll return a subnode. I think we might have called it a minus node in the stuff we distribute. So by the way, so that's the end of the if. By the way, what if it doesn't hit either of those two branches and drops through? What's that mean? Yeah. It wasn't this one, it wasn't this one. It looked like an expression because it had the parens around it, which turned it, the tokenizer turned into an array. But this operator was wrong. It's not something we recognize. So we'll throw, and this, if you look at this error module, we define something in there that's called a Lisp error, which is just simply takes a string. I believe that's the syntax for it. All right, so now we should be able to then, I'll store as the AST, the result of parsing, sorry. I use multiple workspaces, and that just flashed over to a paper we're writing, so sorry about that. So it will parse, let's take that lext string that we did before up here, okay? All right. So let's see, parse array any. Oh, sorry. Because this isn't a module, we have to ci.parse. It's got its own built parse function. Okay. So what's going wrong? First off, let's sort of unpack the error. It's simply saying cannot convert an object of type int64 to an object of type AE. So somewhere it's trying to put an int where it should be putting an AE. Yeah?
So where we're returning a plus node or the subnode, we're putting in numbers.
Yes. Right here, we just took the second and third elements which were 1 and 2. Except those fields are of type AE. So it was guarding when we were putting the wrong types into the fields. What did we not do? What did we forget to do?
Parse.
Yeah.
Oh, yeah, I was just gonna say wrap the expressions that you're passing into plus node and sub node in the parse function. again.
Exactly. Anywhere where these non-terminals, anywhere where the non-terminal that you're defining on the left shows up on the right, that will be recursion. So what we need to do is recursively, we need to store the result of recursively parsing whatever the second sub-expression is, no matter how, or the first sub-expression after the plus, no matter how complicated that might be. We don't care. We just recursively parse and let the recursion do the work. And then similarly, we need to do the same thing here.
Didn't close the.
Yeah, I think I probably goofed on parens. Which one did I not close?
That one.
That one, okay. All right, so now, okay, so this worked. Now, the editor I'm using, just a suggestion. So when you use the Juno package in Atom, there are two sort of consoles you can use. By default, it gives you just sort of a standard REPL. This is sort of its legacy REPL, which I actually like because it does some nice formatting of the output. So if you, so just jumping ahead, if you look at the next assignment, the one due on Friday, at the very beginning of it in the prerequisite part, there's some instructions about how to install and configure Juno or Julia, and some different options you could do with that. Again, you can use Atom, you could use Jupyter, you could write your own in your favorite text editor and run it for the command line. So I'm running it with, if you do it this way, I recommend the legacy mode for the console. So if you look at what it's given back, it's actually showing it as a tree-like structure. It's a plus node. Now if you look at this recursion, this is recursively parsing the second element in the expression. So which case does that hit? Sorry, so this is a 1. Which case does it hit? It recurses back, hits this one. Returns a num node storing the 1. And similarly, here, this recursed and produced a num node storing the 2. So here's our abstract syntax tree. A plus node with a left-hand side that's a number node 1, and a right-hand side is a num node 2. And of course, that can be much, much more complicated. Questions so far? Okay. Now, one of the things that you're going to find as you start, some of the things in the assignment you're going to have to start modifying or adding to the parser. One of the things you find is what we just went through is a pretty straightforward process, right? What's the non-terminal we're trying to process? What are the possible productions? How can I tell which one's which? All right, if I've got a subcase here now, what can I look at the next thing to tell what's what, and so on. This process becomes so rote. There's, I mean, just again, the process, the structure of the grammar drives the recursive structure of the recursive descent parser processing it. And so once you start actually realizing, hey, wait a minute, there's some simple rules to this. I'm just following the rules. So hopefully you'll get that feel as you're working with it. Think about this in terms of the evolution of languages. Once people start doing this, they start realizing, wait a minute, if this is just some sort of rote process, remember, we're all lazy, right, as programmers. What do? You automate it. Okay? So I can actually write code that will take a grammar and spit out the code for parsing that grammar. Does that make sense? Let me say that again so it'll parse. I can write code that will, yes, pun intended, sorry. Can write code that will take a grammar, or a specification for a grammar, and spit out code for parsing that grammar. Okay? Yeah. And these things, by the way, these were done like 40 years ago, so this is not anything new. So people started looking at, well, wait a minute, can I, and by the way, these are called parser generators, generically. People started looking at this first and saying, can I actually automate the process of a whole compiler? And at least they could do the syntax. You still have to fill in all the semantic stuff somewhat more manually. But for the compiler part, or the parser part, you can actually automate it. So people started developing tools that would take a grammar and spit out code. So the early ones were written in C. So slight historical detour here. If I write down here, can you guys still see it? Okay. Unfortunately, the screen takes whiteboard space. Or actually, yeah, let's just do that. Let me just blanket pull this up. All right. So, people started playing around with tools like this, tools for automating the process of creating compilers. And so they came up with a system called, they generally call these things compilers. Okay? So these were called compilers. By the way, you're also used to seeing CC as like the C compiler. But they would call these things compilers. And then somebody would come out with another version that would be another compiler. Then finally there was one that came out under old Unix systems that you'll still find under Linux. That's yet another compiler. All right. Yeah, who says programmers don't have a sense of humor? All right, so it's from, think of it as compiler, another compiler, and yet another compiler, or YAC. Okay, that's what they call it. By the way, that's just the parsing part. The lexical analyzer, you can do the same thing. Right? So, just drop this down. So they actually wrote a tool called Lex that's nothing more than a regular, you feed it a set of regular expressions and what the corresponding token is that should come out. Right? I mean, when you were writing your regular expression matcher in 236, that probably started feeling like there was some routine to it. So Lex is for the tokenizer, and YAC is actually is designed to work with Lex. So Lex and YAC work together. This is the tokenizer or scanner or lexical analyzer. This is the parser. And so using these together, you can actually give regular expressions for your tokens, context-free grammar. Technically, I think it has to fall into the class of what's called LALR1 grammars, if you ever learned about that stuff in 236 or 252. But what it will spit out is the skeleton of a C program for a parser. And you just fill in the actual parts here that we did in our code of what abstract syntax piece to omit in each case. Okay. You'll still find these kinds of things out there. These were the sort of original Unix versions. They later came out, so you're familiar with all the GNU Foundation software, the free stuff. So they came up with sort of a GNU version of them. Lex became a free Lex or Flex, and YAC, I'm not joking, there's a tool called Bison. Okay, more puns for the day. So if you look in most Unix systems, you can actually find Flex and Bison as free lexical analyzers and compiler generators. If I was to do this with a modern system today, there's something called ANTLR. I forget what the acronym stands for. It is slightly tortured. ANTLR is actually something that's Java-based that can be used to create automatically generate parsers. So just be aware that these things are out there. Although we're handwriting a parser, there are tools out there that will do a lot of this for you. All right. So we've now written the part for parsing. We need to actually, so we can check that part off. we've got our parser, and it's now producing an abstract syntax tree out. Now we need to write the calc part of it. So what's calc take in? Right, the abstract syntax tree. So let's write function calc takes an abstract syntax tree, we'll just call it AST, which is of type, what actually, in terms of code, what type is it? Yeah. Yeah, it's one of these parsed AEs. So it's going to take in one of these, which is going to be in one of these flavors. So the first thing we're going to want to do is actually determine which flavor it is. So let's play the same trick here. Not trick, but use the dispatching. If we try to parse, if we try to calc, and it's a num node, so everybody see what we're doing? We're going to have a calc for a num node, calc for plus node, calc for subnode. So calc for a num node, what do we want to return? What does it evaluate to?
The number.
The number that's stored in the node, right? That's all you do for literals. Right? You just simply return them values. So return ast.n, so it's the n field. Question, or you okay with this? Yeah.
Wouldn't calc, like, wouldn't the argument be plus 2, 3? What's the argument for calc? It's just.
So a calc is an abstract syntax tree, which could be any one of these. Right? So it's going to be one of these, which could come in one of these flavors. And so we're writing each of these cases, and we've only written the first one.
I would think the argument would be plus 2, 3, and it would return 5.
Oh, but if it was the case like this, where suppose the input was just 5, then that will parse to be a num node, and then that would be, and then we would just return that value. Right? So we haven't yet gotten to the plus and minus cases yet.
So AST is just Julia's way of saying we're passing in a struct.
Well, yeah,
Something of this type.
I'm just choosing the variable name AST for readability.
that's not
There's
like
nothing in
keyword.
that. No, yeah, there's nothing magic about that. I'm passing in a parameter of type num node.
Okay.
And num node was one of those structs.
So
I'm just calling it AST for readability.
Oh, that's the variable.
That's the variable name.
Gotcha.
Okay. I could call this, whatever I want to here, right? Yeah.
Was n what we called the number?
Yes.
in
So
the
if you
string?
actually, if what came in was a num node, so if we look back, num node had a field called n, and that's what we're returning. Okay. So now, yeah, let's take the plus and minus cases. So we haven't finished yet. We've got to write one for each case. So each case of the abstract syntax will have its own separate calc function. Think of this as just recursing through a tree that's a mixture of different types of nodes. Every time, at every node, you're going to determine which of the different flavors is this, and then you'll have a different piece of code for handling each one.